Hi, this is going to be test prep for test number 7 in 2018 for ENGPHYS 2P04. This was test 6 in 2017. So we are going into discussing shear this time, and we've got a 10 centimeter cube, and it's made from a material with a Young's modulus 10 gigapascals, Poisson's ratio 0.4. One corner of the cube is at the origin, and the opposite corner is at this, so that just to set it up, the z equals 0 surface of the cube is fixed. That's the bottom surface, and the cube is simultaneously subjected to shear in two directions on the opposite z face. And they tell you what the strength of the shear stress is, so we don't have to divide that by the area. We've already got it in force per area. The cube is also subjected to stresses on the other faces to place it into pure shear static equilibrium. Okay, so first off, calculate the shear modulus. If we go to the lecture notes, this is defined at the beginning of the shear stress and strain section. And shear modulus is the Young's modulus divided by 2 times 1 plus the Poisson's ratio. So that's not so bad. We could substitute in the parameters that we've got to figure that out. And E is 10 gigapascals, Poisson's ratio 0.4. Which means G would be equal to E over 2 times 1 plus nu. Okay, so that tells us it is 0.357 E10. So that would be 3.57 E9. .57 gigapascals. Next part, determine the 3 shear strains, gamma, xz, yz, and xy, that are produced by this stress configuration. Okay, so the setup where you just have force on the top, and that by Newton's second law causes with no net force, requires a force applied at the bottom to keep it from moving, would by itself create a torque about this object, and that would cause it to rotate. So to get pure shear, you actually have to have complementary forces applied on the sides, and that's the situation of pure shear static equilibrium. So if you have a shear force on the, I guess if this is the y direction, on the y face in the x direction, then you need a force on the x face in the y direction, which is going to create the same stress. So the shear stress on the y face in the x direction has to equal the shear stress on the x face in the y direction. That's what's required to create no net torque. Okay, so that's what requires that the shear stress is symmetric in applied to an object externally. Okay, so that's what we've got for this pure shear setup. And then once you have that pure shear setup, that's the situation where you can say that the entire strain that shows up is just from the shear stress. So you can figure that out by taking the shear stress and dividing by the shear modulus. That'll give you the shear strain, which for, let's say, yx would be the x displacement on the far y face. Okay, so let's apply that to this particular question. Pure shear, so we've got that tau xz equals tau zx, and that one is the one that they gave us in the question. So that is 1 gigapascal. And similarly, tau zy equals tau yz, which is 500 megapascal. And in addition to that, we know that tau zx would be equal to the shear modulus times the far x displacement on the z face. So this is the xz shear strain. Yeah. So I guess I should say the Zx shear strain, but it's symmetric because the stress is symmetric in this pure shear static equilibrium situation, symmetric and uniform over the entire cube. So that gives us this setup, which we can use to figure out what the delta x is on that far, in that far position. And similarly, we've got tau zy would equal g gamma zy, which is G delta Y over the Z length. Okay, and that asks us, and those are the strains that we would need. The other one would be the strain on the X face in the Y direction. But since we're not applying anything in that setup, that one is just going to be 0. Since tau xy equals 0. So there's no need for that to show up from a reaction force perspective, because there's nothing that we're applying if we've got our pure shear static equilibrium. Okay, so on the X face in the Y direction, yeah, nothing going on there. So to quantify this, substituting in some numbers, we can say tau Zx is equal to 1 E9, tau Zy is equal to 5 E8, and then and L is equal to 0.1. So let's just call that Lz. So then we've got dx at the far point is equal to Lz times tau Zx divided by g. dy is equal to Lz tau Zy over g. And yeah, okay. Oh, I guess first we need to find out the strains numerically. So then let's go and redo this. Instead of solving directly for the displacement, let's go ahead and say that I guess we'll keep this and we'll come back to it later as a check. So gamma Zx is equal to tau Zx over g, and gamma Zy is equal to tau Zy over g. Okay, cool. So there's our shear strains. Next, find the displacement. Okay, that's what we just did in the X and Y directions. Superposition means you just add the displacement of the X point to the displacement of the Y point, but since they're in different directions, the adding is just as, by adding with vectors, it's the displacement we found in the X direction is the X displacement, and the displacement we found in the Y direction is the Y displacement. All right, finally, verify your answer for part C using FlexPDE. And we're going to need to show a picture of the original and the deformed shape, report the displacement, and show the full code. So what we're going to do is come up with FlexPDE code for making this happen, and we've got a new problem here in FlexPDE. So we're going to say maybe T07 2018 video, and let's just build it all up. So this is a completely new file in FlexPDE. Let's get rid of all the stuff we're not going to need. It's not going to be time dependent, so we won't need any of that time stuff. We are not actually going to be using a monitors section, so I think we can get rid of that. And we're not going to need constraints. We're definitely going to need definitions and a select section. So let's see, that should still work. Okay, great. Now, right. So let's go with Cartesian 3 for a three-dimensional simulation. Then we're going to use U for the X displacement, V for the Y displacement, and W for the Z displacement. Then the actual equations are, now all of this is explained in the lecture notes. You can just copy in some code if you want to skip all of this. I'd suggest that you at least once go through building up how what the code is going to look like. So if you set the net force in the X direction equal to 0, and then you use some linearizations and express that in a per unit volume setting, then you come up with an expression kind of like the following, which says that the net stress, the stress derivative with respect to X, plus the YX stress, or XY stress, which, since it's symmetric, with respect to Y, plus the derivative in the Z direction of the XZ stress is equal to 0. That's our per unit volume force equation. Then similarly in the y direction, or for the net force in the y direction, we'd have dx of s xy plus dy of sy plus dz of s yz. And in the w direction, in the z direction, dx of s xz plus dy of s yz plus dz of sz is equal to 0. Okay, so that's the net force is equal to 0, but we need to, since this isn't directly in terms of the displacements yet, we need to go back and kind of build this up in some order that explains how these stresses are themselves related to the displacements. And you could kind of jump right into this and try to substitute them all in, but what I'm going to do is express how those are related to the strains up here. So we've got the stress related to the strain from what we already know in a couple of different ways. So we know that the let's see here. Yeah, so for shear, we know that the shear stress is related to the shear strain through the shear modulus. And so we could say that Sxy is equal to G times epsilon xy, and Sxz is equal to G times epsilon xz, and Syz is G times epsilon yz. But if we're going to express these as engineering strain notations rather than the true strain, or rather, so this is what it would be if it was the engineering strain that we've got up here, but in terms of the true strain, then we need to have 2 times G. Then for the axial parts, so this is the shear stress, shear stress strain relation. We're going to need to know the axial stress strain relation, which would be, these are both Hooke's law, so maybe we'll put a Hooke's law. And then down here we will say that's Newton's second law per unit volume, so these are Hooke's laws. And then we're going to get the axial one, it would be Sx is equal to C11 times epsilon x plus C12 times epsilon y plus C13 times epsilon z. Where's this stuff come from? This is the axial part when we introduce stiffness and compliance matrices up here. We said that the stiffness matrix can give us the stress from the strain. Now actually, for this kind of material, all of the off-axis elements in the stiffness matrix are the same. So C13 is the same as C12, and all of the diagonal ones are the same too. So maybe we can save a bit of time and just write this out using only 2 different elements there. So Sy is equal to C12 times Ex plus C11 Ey plus C12 Ez, and Sz is C12 Ex plus C12 Ey plus C11, a diagonal element again, times Ez. Okay, so this is the result of multiplying those matrices out. And there we go. So what do we need to define up here? We need to define what the Young's modulus is. How are we going to do that? I guess we don't want to have a symbol which is just E. Maybe that could cause trouble later, so we'll call that, oh, no, we definitely can't use EY. We already did that. Young's modulus. Let's just go for it, E. Okay, so E is equal to 10E9, and nu is equal to 0.4. G is equal to E over 2 times 1 plus nu. I know we already calculated this, but it's sort of silly for us to try to to just substitute in the magic number in FlexPDE when it's very easy to just type out the equation for it again. So then we've got C11, the first component of the stiffness matrix here, is supposed to be equal to, from reading this element off, it would be E over 1 plus nu times 1 minus 2 nu. Let's get that all on the same page here. C11, E over 1 plus nu times 1 minus 2 times nu. And then we're going to multiply that by 1 minus nu. And for C12, it'll be the same thing, except multiplied by nu. Okay, so that's that. We're all good there. The very last thing to do is to substitute in the strain definitions. And that would be how the strain in the x direction, strain in the y, and the strain in the z are defined, as well as the strains in the cross direction strains. So this showed up when we were defining the strains down here and thinking about them in terms of derivatives. So the axial strain is the x derivative of the x displacement. So Ex is equal to dx of u. Ey is dy of v, and Ez is dz of w. For the shear strains, we wanted these to be the true strains that we're writing out down there, and that would tell us, so from that definition, we've got that Eyx would be the y derivative of the x strain. So we would say something like Exy is equal to the x derivative of the y strain. But the other thing that we want to do here is express that this is supposed to be symmetric right in the definition. So we'll say that it's dx of v plus dy of u over 2. Then similarly, xz is dx of w plus dz of u over 2, and Eyz is equal to dy of w plus dz of v over 2. So let's check. It's easy to mess this up. We should have symmetry here. So 2 of the equations have w's, 2 have u's, 2 have v's, 2 of them have dx's, 2 of them have dz's, and 2 of them have dy's. All right, so it looks like we have not double counted a variable. We're all symmetric here. Everything looks pretty good. So we should have something that's similar to the equations that were written out in FlexPDE. So xz is dzu plus dx of w all over 2. Yep, that looks good. We've got the same kind of a definition for the matrix elements. It looks like this one's just been multiplied through. And the same differential equation at the end. Okay, looking good. All right, next thing we need to do in the FlexPDE code is make up the geometry that we're going to be working with. And this is a little bit more complicated. So, yeah, so what we're going to be doing is we can still map out a square in the x and y directions there, but we need to have some kind of an extrusion in the z direction. And the syntax for this is in the next part of the lecture notes. So if you go down here, it's under 3D, creating geometries for 3D objects. We've set our coordinates to Cartesian 3 already, and then we're going to need some kind of an extrusion from some named bottom surface to some top surface, and then we can we can specify those in the boundary section as well. So I think that you just can put in the extrusion part without actually changing any boundaries, and then it will still work. Oh, we need to define the name LZ, so let's just do that. LZ is 0.1, and let's see how stuff works. Okay, so we'll need, so contour plots don't work. Let's just get rid of that for now. Okay, simulation ran. That's a big step forward. So now we can include some outputs on things. So we don't need a contour plot. One plot that we're going to want is a grid plot. Grid of X, Y, and Z. This just replots the geometry. So you can plot the geometry and the displacement. And there isn't any displacement yet, so there's nothing nothing weird about that. Nothing actually interesting going on there. Okay, so we set LZ to 0.1, but the other sides are still set to 1. That's because of how we walked this around. So to make this a little bit more flexible, we can name that LX, and then LX, LY, and 0 ly, and then give those things definitions as well. Okay, now we've got a cube because we set it to 0.1, 0.1, and 0.1. Okay, so that's that part. Next, the boundaries. So first let's mess with the Z boundaries. So we can say surface bottom. We referred to bottom earlier, so now we can just refer to it right there and then set up some boundaries. So we could say something like value u is 0, value v is 0, and value w is 0. This fixes it completely on the bottom. And then set some different boundaries on the top. Load W equals 1E9. Let's set some massive stress on the top and just see what happens. Okay, so you see it's starting to pull on this cube. We can set that to 10E9. And yeah, so indeed we've got some stretching up on the top here. And that's great. We can set some, we can change this to the actual question where we've got a 1E9 in the X and 5E8 in the Y, and see what happens. Okay, so it looks like it's folding over, but to do this, it's not actually in pure shear right now. To get it into pure shear, we're going to need to also specify the boundaries on the sides, and this is a little bit tricky. So whenever you specify a boundary, they keep these boundary conditions still exist until you specify another one. So we can specify a boundary in between these different sections. First, let's just add in the keyword line here, which is implied if you just have this point and then a 2 immediately afterwards. So if we do this, then we shouldn't have changed anything. Okay, all good. And now we can specify boundary conditions in between this starting 0, 0 point and then sweeping out from with no y change, but changing the x. So if y is holding at 0 and we're sweeping all of x, then the boundaries that we're setting right here would be the y equals 0 surface. So the y equals 0 surface for pure shear in this particular setup, we're going to need to put a force of 0 in the x direction, no stress in the y direction, but a stress in the z direction, which is counteracting the stress up here that we're applying. So that would be -5E8. Now the problem is if we just do that, then that stress is going to be applied to all the different sides too. So one thing that we can do to get some numeric answers here is include a summary. Report val of u, and then we give it a coordinate, lx, ly, lz. So this would be the x displacement, and then we can do the same thing for the y displacement. Actually, that's the z displacement. Same thing for the y displacement v and the z displacement w. So this should be working out in a summary section there. Yeah. So this is telling us what the displacements are. And right now, it looks like the displacements compared to the ones that we calculated with Maple are a fair bit larger. So rather than the 28 millimeters in x that we predicted, we ended up getting 73 millimeters in x. And that I think is to do with the boundary conditions that we've got set up here. So it's not in pure shear, it's actually moving a lot more than that. So let's continue applying these boundary conditions and figure out which side is which. So this first one is the y equals 0 surface. Then we've got with x held at Lx and y changing from 0 to Ly. This would be the x equals Lx surface. Then we're holding y at Ly and changing x, so that'd be the y equals Ly surface. And then the next one, from this point to close, which is 0, 0, we are holding x at 0 and changing Ly, so that's the x equals 0 surface. Okay. Now we'll set the boundary conditions that we need in between. So on the x is Lx surface, we are going to get a load in W of positive 1e9 to counteract the x stress on the z surface of positive 1e9. And then on the positive y surface, it's equal and opposite to on the negative y surface. And on the negative x surface, it's equal and opposite to that on the positive x surface. So this should now, if we haven't made any mistakes, reproduce exactly the pure shear static equilibrium case. Looks like much more of a pure shear situation. And we've ended up with 28 millimeters, 14 millimeters in, and 14 millimeters in x and y, respectively. Okay, part 2. For the cube in part 1, instead of the shear stresses, place the cube into tension by applying a 10 gigapascal stress on the plus z surface, and keep the z equals 0 surface fixed in all 3 dimensions. First, calculate the displacement that the corner would, of the 10 centimeter cube, what the displacement would be relative to the center of the bottom of the cube if the stress was a uniform stress and the cube is otherwise free. So this is just based on the axial stress stuff, where we were saying that sigma is equal to E. So sigma, let's say Z, is equal to E times epsilon Z. And that would be the 10 gigapascals is equal to E times the delta Z over LZ. So for uniform stress, then we can use this calculation and determine that dz should be equal to sigma z 10e9 times lz 0.1 divided by the E, Young's modulus. And since the Young's modulus is also 10, I guess we kind of sort of was overkill to use this. It's 10 divided by 10 times 0.1 meters, so it's 0.1 meters. Okay, use FlexPDE to determine the actual strain of that corner of the cube in response to the loading. So we'll get our FlexPDE. We'll come back to this same setup that we had, and we'll change the loading condition. We still have it. We have it actually fixed on the bottom, and we'll apply a 10e9 load to the top, and then we'll make it completely free on all the other sides, as the question stated. And we'll come up with this. So actually we had calculated something like this while building up the program in the first place, and now we end up with this displacement. So the W is not quite 0.1, but it's a little bit less. It's 5% less, and it's moved in the x and y directions. We could have figured that out earlier from Poisson's ratio, that it should end up moving in a bit at the top, but what we wouldn't have predicted is this, that it moves a little bit less. Does the result from part B match the calculation? No, it doesn't. And the reason is to do with these anchors. So we're 5% different because of this kind of resistance to moving in at the bottom. Because we're stopping it from moving in as much as it would like to otherwise, then it's not able to go as far in that direction as it otherwise would. So this is kind of this creates a higher stiffness. And we can check this by freeing it in the x and y direction on the bottom and seeing what happens. Now the z displacement is exactly 0.1. The x and y displacements are sort of all over the place. They're not symmetric because we didn't hold anything still in x and y. And if you want to constrain those, then you can do that too. So now we can, on the y = 0 surface, say that that's not moving, and let's say the x = 0 surface, say that that's not moving in x. And now with those sides fixed, the opposite corner is going to tell you exactly the kind of displacement if the origin is fixed. So that gives you a 0.04, which is the Poisson ratio times the strain times the displacement in z, and that's not a coincidence. That's what you would have figured out for your perpendicular strains. And the z strain, as before, gives us exactly the calculation. So the reason that part B doesn't match with part A is entirely because of the anchor condition.